Welcome to Calculus. Today we will investigate graphing tangent lines of functions that are made up of different products or quotients. And we'll be focusing on using the product and the quotient rules to help us find the equations for those tangent lines. Let's take a look at a product. So f of x here is this function x plus 1 times x squared minus x minus 11. So I can see that that's a multiplication of two separate functions. And so as I look at it, that just makes me think, I'm going to need the product rule. So before I even start reading, I just want to remember the product rule for differentiation. So that would say if I have a function big f of x, which we'll consider is our small f of x. So one thing I'm going to do is I'm just going to overwrite this. This is really big f of x, that original function. And the reason I changed the name there is because big f of x we would consider to be f of x times g of x. So small f of x times small g of x. Well, if I were to take the derivative of big f of x, this again would be our product rule. So the same one we've been using. So it's the original function f times the derivative of g plus, so it's a sum, original g of x times the derivative of small f of x. So we'll be using that, and we can, in fact, start setting it up. Let's go ahead and take the derivative of our function here, and then we'll look in these a, b, c, d, e, f to see what do we actually need to do with the derivative. So I'm just going to mark stuff here. I'm going to define f of x as that little binomial x plus 1. So the original f of x is going to be x plus 1, which means its derivative, if I take the derivative of small f of x, that's going to be the derivative of the linear term x. That's just 1 plus derivative of 1 is 0. So that's just 1. Similarly, let's define g of x as that quadratic function, so that if you're thinking like factors, that's the second factor in the product. So if the original function small g of x is x squared minus x minus 11, the derivative of g of x, if we apply our simple power rule, is going to be old power 2 as a coefficient, x to the power of 2 minus 1, minus the derivative of the linear x is just 1, and then the derivative of negative 11, that constant is 0. So that's going to give me total derivative of 2x minus 1. So I'm ready to plug into my product rule here. So original function f of x is x plus 1. Derivative of g of x is 2x minus 1. Original function g of x is going to be x squared minus x minus 11. And then the derivative of little f is going to be just 1. So we'll go ahead and FOIL out, and then we need to combine like terms there. So for my first FOILing here, double distribution, I'm going to get 2x squared minus x, and then for my inner and last terms, plus 2x minus 1. And that's going to combine as 2x squared plus 1x minus 1. So we do need to combine that as well with the result from the other product, which is just x squared minus x minus 11 times 1. So that's going to be plus x squared minus x minus 11. Now we need to combine the like terms within those two groups. So 2x squared plus x squared is going to be 3x squared. X minus x, the linear terms cancel out there. And then I'm left with negative 1 plus negative 11 is minus 12. So that's missing its b term, its linear term. Well, there's my derivative. So the derivative of this product is going to be 3x squared minus 12. And let's take a look at why we need to know that derivative. How are we going to use it? Well, let's take a look here in part A. Part A says find the points, if any, at which the graph of each function f has a horizontal tangent line. So here's really our use of the derivative. Remember, a horizontal tangent line has a slope that equals 0. And then when I think in terms of, okay, what's the derivative of a function really telling me? Well, it's telling me in general, what's the slope of the tangent line at any x value? So what we're trying to say is, okay, where is the derivative of the function equal to 0? And for that part, what I need to do is take my derivative function, which I've got here just calculated, and I need to set it equal to 0 and solve. And that'll show me the x values at where there's a perfectly horizontal tangent line. Well, let's do that. So I see that I've got a factor of 3 that I can divide out of really each term on both sides. So what that's going to give me is simply x squared minus 12 divided by 3 is minus 4 equals 0. And that's a difference of two squares quadratic that I can factor as x plus 2 times x minus 2. And if that equals 0, really what I'm saying is, if I look at this left-hand factor, what plus 2 would equal 0? Well, that's got to be negative 2. So one of the solutions for this is that x is negative 2. From that right-hand factor, x minus 2, what minus 2 would equal 0? Add 2 to both sides, I get x equals positive 2. So those are the two x values where I've got a horizontal tangent line. What I need to figure out is what's those y values. So I'm going to create a table here. And really, I need the table anyhow for part E here, because I got to graph the function. So I'm going to start setting it up right here. And we can calculate here for just these two x values to begin. So the function is x plus 1. I'm going back to the original function times x squared minus x minus 11. And I'm going to leave some room because I know I got to graph this one. So I'm going to put negative 2 there and then skip down a little bit and put positive 2 and just calculate those specific values for now. So that's going to be negative 2 plus 1, which is going to have the value of negative 1. And then negative 2 squared, which is 4, minus negative 2. So the double negative means plus 2 minus 11. So that's going to be negative 1 times 4 plus 2 is 6, minus 11 is negative 5. So negative 1 times negative 5 is positive 5. So I've got a tangent line at negative 2, 5. And I'm going to go ahead and sketch that in. And I'm going to give its equation. That's part B there. It's going through the y value of 5, so it's the equation y equals 5. Let's catch the other tangent line by doing a similar substitution now with positive 2. So that's 2 plus 1, so that's going to be 3, times 2 squared minus 2. So that's 4 minus 2 minus 11. So that's going to be 4 minus 2 is 2. 2 minus 11 is negative 9 times 3 is negative 27. So I can find it positive 2, negative 27. I got to estimate there. I have a second horizontal tangent line. And I'll put its equation y equals negative 27. So that takes care of parts A and B. We'll come back to parts C and D. In fact, what we should do to figure out parts C and D is graph the derivative. So the derivative is this function 3x squared minus 12. So that means that this function is going to have its vertex is going to be down at negative 4, because I can really think that this is 3 times x squared minus 4. So actually its vertex is at -12. That's that y value. In fact, let me pick up green so that it's clear this is the derivative. Derivatives are green. And then from the factors, I know it has zeros at -2 and 2. And then I can just sketch in this parabola. So that's the derivatives graph. So I'll just put that, that's the derivative of big F of x. Well, the reason I put that there is because it shows me where are the derivative values greater than 0. So I'm going to highlight here in green, that's that part in C. So I'm looking at the derivative function. It's really on the left of -2 and on the right of +2. So I can record that as an interval. In fact, the union of two intervals. So on the left, it's from -infinity to -2. And then I'm going to take a union and pick up at +2 to infinity. So you might be asking, what happened to that interval in between? Well, that's for part D. Notice part D says, where's the derivative's y value going to be less than 0? That's that nose of the quadratic. And that is between -2 and +2. We'll come back in part F and say, okay, what can we say about the function based on that? But we need to do this part E. So part of it we've already done. We've graphed the horizontal tangent lines. We need to see the function itself. So I'm going to turn back to my table here, and I'm just going to put some other x values, -3, -1, 0, 1. And let's go to 3. And I'm going to head over to Desmos just to catch a table real quick. So I've written down the original function. Let's go grab a table. So this is f of x equals, again, this is the original. So x plus 1 times the quadratic x squared minus x minus 11. So I can see it's a traditional cubic function, left arm down, right arm up, got a curve in the middle there. But again, I want a table. And let's put our -3 value there, and then we'll go past to +3. So I can see that this is a good place to note that there's a horizontal tangent line at -2,5, because that's a relative maxima. And if I were to zoom out sufficiently to see that lower point at 2, -27, that's a minima. So I can see why there's horizontal tangent lines there. Those are extremes. I'm going to record this table. So -3, -2, -2,5, -1, 0, 0, -11, -1, -22, +2, -27, +3, -20. So that's what I need from Desmos. I'm going to go back to the notes to graph that same function. So the outputs, again, just what we recorded, -3, -2. So I'm going to graph that one. That's about here. I got the point -2,5. And then it goes in a decreasing manner after that. So -1 is at 0. That's a actual 0 of the function. 0 is at -11. That's the y-intercept. I'll just estimate right there. 1 is the value -22, which again, I got to estimate. Then we do actually have 227, -27, and then 3, -20. So that allows me to sketch this cubic function, which is again the original function, big F of x. And that completes that part E, really all the way A, B, C, D, E. Our last part is part F, to describe the graph of F based on what we said in part C and D. So that's really saying, okay, how does the sign of the y value of the derivative help me interpret the graph of the original function? Well, if I highlight the part of the function where the derivative is positive, again, that's this part on the original, so on that left arm, and then also on this right arm. And what I would ask you to consider is, what is the sign of the slopes of the tangent lines on those green highlighted parts? Well, it's an increasing part of the graph, so the slope over here is positive. Slope on the right side is similarly positive because that's an increasing interval of the graph. When I compare that to the part of the original function on those x values where the y value of the derivative is negative, so that's this between negative 2 and 2, I see that on my graph, the slope of that portion of the tangent lines is negative. And so that's a feature that we can analyze based on looking at the sign of the derivative. Well, that tells me about the sign on the slopes of the tangent lines on the original graph. Well, let me let you go work on some of your products functions to find horizontal tangent lines and also to graph the derivative in the original. We'll come back in a moment to look at a quotient, but for now, I'm going to let you work on yours. See you soon.